it's an ongoing discovery, and I'm sure there are many more discoveries to be made, not just in relation to this particular event, but to the events in that particular time of geological history. Because it is an interesting time, and we have all the facilities in Adelaide to look at that. If we think of deep geological time, it goes back right through to the start of our Earth forming about 4.6 billion years ago, and the moon formation and so on around that early time. Already the Earth, from the minerals that we have here, the zircons, indicate there was water on our planet. So we've had water on our planet ever since the word go, virtually, ever since things cooled down and away we go. We're here in the present, and the Phanerozoic, or the time of visible, phanero meaning visible zoic life, visible life known as the extant fossils that we have with shells, etc., is now known to have been preceded by a short period, or perhaps not that short, Ediacaran period, the first multicellular animals which did not have any spines, did not have any skeletons, external or internal. And so there was a big revolution, of course, at the beginning of the Cambrian, when all of a sudden 5 phyla had to develop either skeletons or had to dig away from their predators because the big eye had been developed. A big animal that is now known to have huge eyes and recovered, structures recovered in Kangaroo Island, just offshore, in the Cambrian deposits, indicate that predation began. In other words, remote sensing, and you have animals that could look at you in the distance and direct their attention to you and have you as a meal. In order to do that, then you had to either develop skeletons, so that you had the trilobites and the echinoderms, so in developing spines and developing external skeletons, like the ancient crayfish equivalents, crab equivalents and so on, or you had to have worms or some animals which would dig down underneath, and the beginning of deep burrowing begins at that time. So I'm kind of skipping along to there to put you into the picture that in fact this period of time, which is at the end of the Adelaidean system, and we do have some Cambrian in South Australia, on Kangaroo Island, as already mentioned. So we have this long period of geological time. Those of you that have been to Mount Painter or wish to know where would Broken Hill rocks fit into this picture, and the Gawler ranges and so on, fits into about this area here. So I've got here Mount Painter, but in fact most of the ironstone, major ironstone formations are about 2 billion years old, 2.5 billion years, so about here. So that gives you a feeling too for increase in oxygen content. And the increase in oxygen content plays an important role. Before animals had any lungs, before the evolution of animals with internal structures called lungs, they had to breathe through their skin, like jellyfish do, like seabirds do. And worms, flatworms and so on, don't have lungs. So they've got to imbibe their oxygen for their metabolism through their skin. Therefore there has to be enough partial pressure, as we call it, enough pressure of oxygen, enough oxygen in the atmosphere to allow that to happen. So it wasn't for a long time that the Earth had anywhere near enough oxygen for that to occur. So there was no chance for any multicellular organisms to have evolved. You follow? Everything sort of starts to form. The last few years we've had this wonderful assembly of data from left and right and geochemistry and isotopes and so on that helps to fill in the jigsaw puzzle of what early life was like. So without further ado, I'm going to sort of launch myself into this part and let you know what happens in this part. To begin with, the outline of my talk, and I have a slide here from Alaska to remind me that really this is a time of glaciations. We've had several major ice ages in that part of the period. Sturt Gorge here in South Australia illustrates wonderfully the Sturtian Ice Age, and those equivalent rocks of the Sturt Gorge type occur right through the Flinders Ranges, the massive thicknesses of that at Arkaroola and to the west of Arkaroola. Then there was a period of little ice or of no ice at all, and then a new ice age came, and that was the period of the of the Alatna glaciation or the Marinoan glaciation, which you can see down at Merino Rocks. If you were to, well, I've already mentioned Sturt Gorge. Sturt Gorge rocks are overlain by the Tapley Hill formation, which is there in Tapley Hill and also in the new cuts on the new freeway. And you can recall surely that those rocks are all grey in colour, dark, bluish, grey, dark. No evidence for any oxygen in that water body. But as you come towards Merino Rocks, you start getting red beds. You start getting rocks which are intrinsically red. And by the time you end up at Hallett Cove, you're really dealing with sandstones which are yellow and shales which are red or purple in colour, indicating lots of oxygen in the atmosphere. So there we witness that increase of oxygen in the atmosphere, so that the shallow parts of the marine environments had enough oxygen to create the oxidized form of iron oxide. Instead of ferrous, it becomes ferric or rust, if you like. Right, so I'm going to mention some of these points because we have evidence that there was already ice present at that early time. Let me launch straight into it. This is the area we're talking about. So this is South Australia, basically. And we're talking about the Gawler Ranges in red there, in pink. The Officer Basin to the west was a marine environment, and there are drill holes there which we were able to recover significant deposits of the ejecta from there. And the Adelaide geosyncline, or trough, which is over here. The actual outcrops are shown in triangles or in circles indicating drill core or outcrop. And I'll refer to them. We don't see, sadly we don't see any dots south of Pitchy Ritchie Pass or Quorn, because simply rocks of that age were removed by erosion before the Cambrian was deposited on top. So there's a missing interval there, and so sadly we don't have any evidence. But I will talk at the end of the lecture, I will draw analogies with overseas examples of this part of the geological spectrum, this part of the geological column. Right, so this part being, if we begin with about 630 million years ago, we have the Alatna glaciation down here, and this is all in reds in the oxidized form, the Brachner formation. Brachner Gorge, if I were to tip this sideways, you'll see that the coarsest beds of the ABC range quartzite stick out as the ABC ranges. They're quartzites or cemented sandstones. Before that you have shales and sandstones. And then above that appeared on the Bunyaroo formation, which is again a very fine shale. In other words, waters became deep, relatively deep, and it's there that one finds ice-rafted detritus and the Acraman impact ejecta horizon. Well through then continues on, and you have the earliest ediacaran biota up here, shown as an example here with Dickinsonia. And by the way, Dickinsonia, I had the pleasure years ago now in Bathtub Creek there, and it tells you with the location, north of Alpena Pound, were almost short of a metre, about 90 centimetres long, this flat worm. With that sort of structure. So it's quite impressive size these ones get to. So that's by the time you get into the Pound here, the Rawnsley quartzite, and then overlying this is the Cambrian. So the Cambrian there with all the burrowings and all the shellfish and all the limpets and brachiopods and other shelly organisms up there, trilobites of course, and so on. So we're going to first of all see the evidence of the ice-rafted detritus. These two examples were found after quite a few years, and only when people were very sceptical of our findings. They said, oh, no way. I mean, we had these isolated pebbles, a few centimetre pebbles sitting in this very fine silt, and people in the museum said, well, you know, one pebble doesn't make a spring, one swallow doesn't make a spring, so how do you know this is ice rafted at all? Well, we had an honour student, a lady honour student, who went out and searched and found about 3, 4 more, not many, but again, they're not where they should be. They're not where they should be. How do you get in something which is very fine and silty, deposited in very, very gentle, quiet water, suddenly you have something which is either been thrown there somehow or had a rafting agent. Now today you might ascribe such a rafting agent to kelp. Kelp, after all, if you've been down to our big bull kelp areas and down in the south coast, the southeast of South Australia, you'll know that built in the root, it would pull out and the storms will pull them out, and there's a whole root hold fast that the kelp has, and it could have pulled out one of those. So today we have that bull kelp analogy, but bull kelp really, if it is hanging on, would hang on to solid rock, not to a pebble, so it would have very angular ends, and I do have samples in my garage with the angular bits of bull kelp holdfast. Another reason might be that it would have been thrown out of a volcano. Well, there's not volcanic rock to begin with, so that's out of the question. And perhaps tree roots too. I mean, in modern times, tree roots, but we didn't have trees in those days, long before you had major land plants of that type. So really it excludes everything except ice. But you have always the skeptics, and thanks to the skeptics, I must say, it's nice in science to have the skeptics, because then it makes one look even closer to what the evidence is and try and find more. So we did that, and we have ended up finding this sort of thing below the meteorite impact horizon, Acraman impact horizon. So a metre or so, what did I say, 2 metres below the impact horizon, you have this squarish, rectangular edged gravel. How do you get a rectangular edged gravel sitting in fine siltstones deposited in quiet marine waters? Well, think of a dirty ice block. Think of a dirty ice block. This was held together, dirty, I mean dirty in the sense that you had morainal material, glacial material ground up and so on, as glaciers have. If they're grinding through terrain, ancient terrain and so on, there'd be a lot of material either collapsed onto the surface of the ice or encumbered from within. It'd be unsorted, it'd be debris of various grain sizes. Then you've got to congeal it enough. What was the cement that held it in place so that it would drop onto the ocean floor and preserve that structure? If it was just, if whatever it was, just fragmented and so on, we end up with a heap. You'd have a heap here, not a crisp-edged assemblage of coarse and fine debris. So interpretation here is an ice block. And that is before. This is after. This is 8.5 metres above the Acraman impact horizon. That's below the impact horizon. So already we have some evidence, and there's more to come, that in fact you had ice floating around at that time. There had been river ice or shore ice, as you have in eastern Siberia. There are no major glaciers coming down to sea level in eastern Siberia, but it's very cold, and the rivers freeze, and the shoreline freezes, so you have coastal ice, and you've got river ice and so on doing the job of icebergs. However, this evidence is iceberg evidence, because we have what we call till pellets. Now, to explain how till pellets form, for glacial ice to move, not shore ice or river ice, but for real glacial ice to move, it's a rock. It moves only by recrystallization, as if it was a metamorphic rock. In fact, metamorphic petrologists study ice movement because they have analogies with silicious rocks that do the same sort of process of recrystallizing. So with ice moving, basically where the ice under pressure, it dissolves, it liquefies, and it refreezes. It refreezes, and so new crystals form. But the new crystals that form lack the debris. The debris that's carried in the original ice material is no longer incorporated into the new crystal. New crystal is clean and nice, icy crystal without any debris involved. So the debris gets locked in the triple junctions and the places between the crystals. And there's enough pressure in the glacial movement for that pellet, that interstitial material to have enough cohesion, so when the ice melts, the pellet drops down to the lake floor or ocean floor, or wherever it happens to be. Early description of this was by Tom Ovenshine of the United States Geological Survey, and I learnt that from him because I was co-scientist with him on a deep sea drilling expedition. it's another story. And he said, well, he actually published the first paper on that, on till pellets, and he recorded them in the glacial lakes in Alaska. And he saw the process by which they're formed. He saw them coming off the glaciers, coming down into the lake. He saw them there, and then he, by looking at this, at the lake floor, found that they're full of these till pellets. You can find till pellets at Howard Cove, because there's an old Lake Acraman glacial deposit there, and you'll find, if you look closely, till pellets there, and the same thing occurs in the sturtillite elsewhere. So we now understand that this is a very good indicator of glacial ice, of real recrystallizing type glacial ice. Okay, then came the impact. So we now have the sequence where we have a major impact. That's not a, you mightn't be able to see it, but Lake Acraman is there, the Gulfs, Adelaide Fold Belt, well over there, about 300 kilometres away. Not 30, not 3, but 300. So we're not talking small babies, we're talking big bangs. It is a deeply eroded remnant at the moment, so in fact we have a few kilometres of crust that has been removed since. There is a night thermal image, one of the earliest, from the satellites. The US produced some night thermal images. What these do is basically the infrared image. And infrared cameras, as you may know, you might have one yourself, actually records the heat radiated. And the heat radiated from a body of water at midnight is still there, whereas the land has lost its heat. Rocks very quickly cool down, as anybody who's been camping knows, whereas if you're at sea, you've got that moderating coastal influence, and so water doesn't. So the radiation is much greater from the Gulf. There's Spencer Gulf, top of there's Seduna about here, and there's a big bullseye structure, because it records, some of these are the lakes, Lake Torrens there, for example, moist parts and so on, but here you have this bullseye structure which records the variations of solid dry rock with damp crushed rock. All right? And it was an early one that George Williams 94, who used this in the publication to display how wonderfully the material shows, the image of the night thermal image shows up the structure of the impact site. The earliest ejecta were found at Pichirichi here, the ejecta, and the other crosses are where they've been found elsewhere since then. And the story is then as follows. Basically, we had the meteorite impact, and I've added a few icebergs and a few blocks of ice because we now know there was glaciation on that surface. A transient cavity, that's the cavity formed initially as about 40 kilometres in diameter. And with the transient cavity, then you have the repercussions, the tremendous oscillations of the crust that lead to a final collapse crater of estimated about 90 kilometres in diameter. So it's a big fellow. The asteroid itself is estimated to be about 5 kilometres in diameter, 4.5 to 5, which is about half that estimated for the end of the dinosaurs. The Chicxulub asteroid that hit Mexico at the time of the end of the dinosaurs and end of the ammonites and many other phyla as well. It's not just the dinosaurs. The top 2 metres of ocean water was poisoned in the process. So don't forget, it's not just the end of the dinosaurs. A whole lot of other things died off as well, poisoned by the nitric acids and so on, created by the infall through the atmosphere. Okay, so it's about half size. However, it's located, we found it's located paleogeographically in equatorial zones. So being sub-equatorial, it would have affected both hemispheres. Northern hemisphere, southern hemisphere at the time, and therefore would have played a more important role in any biological and ecological effects. So we had that, and we had lots of material exposed. Then 500 million years of erosion, 500 million years ago, there was the folding. This marine environment ceased to be marine, and the folding of the Flinders Ranges occurred. We call that the Delamerian orogeny, after Delamere down at Eyre Peninsula, the intrusion of the granites, Victor Harbour granite, Manum granite, and granites through and Mount Painter, etc. And then lots of erosion since that time. So what you have is not the crater, sadly. It would be nice to have had some crater melt rock, as you get in other meteorite craters, but this is obviously below that. However, the rocks are intensely fractured, and I'll show you some of that effect. So George Williams is the one who described the evidence for the impact here, whereas my and students found the debris layer in the Flinders Ranges, and it was that combination of evidence, both from the remnant scar of the asteroid impact and the remnant debris left behind by the in the Flinders Ranges, buried there. And by the way, I've carried this from home just for you to see. If you don't believe anything, you might believe a solid lump of rock. There it is. It's all very well to have the layer which is mainly sandy, but how do you get blocks of volcanic rock like that sitting in that sand? Okay? And those blocks of rock increase to football size and double football size. So I couldn't carry one of those, and it's under my desk at university. Okay, so we also have that sort of stratigraphic position we pointed to you here. In the Officer Basin, there is an analogous drill core which we have the same material. There is the present day topography, in false colour of course, present day topography of the Acraman depression. And so inside it's about 20 kilometres of this fractured rock in diameter, with the harder rocks around, and there is another ring further outside that. But it's quite impressive even today. Quite impressive even today. So there is the material from inside. George Williams found this well before we had the discovery in the Flinders Ranges, and he went out there and he recognised that the volcanic rock was surely volcanic, all a range of volcanics, but it had been intensely fractured. And the upper part, there's a bit of a crust there with lichens on it, but just crushed to smithereens, really, to a finer dust, still with fragments of coarse material in it. So that's the dacitic. Dacite is simply it's the volcanic equivalent of a granite. Okay, so the volcanic equivalent of a granite. A granite melt were to come out on the surface of the form what we call a dacite. Lots of quartz and feldspar, and very little heavy minerals and iron oxides and so on. Okay, one of the distinctions is this feature in quartz and also in minerals like feldspar. But quartz has not any cleavage. If anybody's done if you've had quartz and you bash it with a hammer, it won't break into nice cleavable bits with smooth faces as if it was calcite or something like that, or a feldspar. It would shatter like glass. Conchoidal fracture, we call it. Conchoidal, like a conch, so the conchoidal fracture. So to have this sort of feature in quartz indicates something very different. In fact, these are not cleavage lines, but they're planar deformation lamellae, as they're called, PEFs, features, which are caused by the intense pressure of the meteorite impact and the formation of a coesite stusovite, a higher density form of silica. Instead of quartz, it becomes SiO2. Chemistry doesn't change, but it transfers itself into a much denser form of SiO2, of silica. And that is a different refractive index, so it gives rise to these lines. And the more of these intersecting lines you have, the more intense the impact would have occurred. We know this from studies of other well-known impact craters through Canada and United States and South Africa and so on. So these planar deformation features are well known. Just recently we had a publication again came out by a person studying Toba, the super volcano in Sumatra, which erupted, let me not get it wrong, something like 73,000 years ago. Still within human history, but again, that's another story. So Toba, the intensity of that eruption was strong enough to create these sort of lamellae in the quartzes of the Toba volcanics, as it turns out. Okay, let's move on. So what we have today is, therefore, there is the scar, there is the distribution, at least as we know it so far, assuming a uniform distribution. We have no reason to think it was otherwise. By the way, if you have a high velocity rifle, or you have something with very high velocity hitting a surface at a low angle, even the angle has to be lower than 5 degrees for it to become oblique. Everything else will be round. For that reason, all the craters in the moon except 1% are round. So even a random distribution of impacts onto the moon will still create a round surface, except, as I said, for 1% or 0.5%, which have to be very, very low angle to then create an elongated crater. So we don't have any evidence for that. We don't have enough outcrop to really do anything more to say the direction of that impact. But anyway, we certainly have that as a known thing. This was taken just 2 weeks ago. I was showing 3 couples through the Flinders Ranges, and I was able to be photographed sitting down there at the Acraman ejecta layers, just on the north side of the Bunyaroo car park. And the parks people have actually installed site 1 there, labelled Acraman debris, with an arrow pointing that way. So, as I said, the Bunyaroo is about 300 kilometres from the impact, and clearly, and that's further along the outcrop, you can follow it along and you get, it widens and thickens and thins. There it is in more detail. There it is, one of the bigger blocks in that slice through, the 6 centimetre scale. But as I said, you can come here and have a look later at this one here, because I suppose feeling is believing. If you don't believe that I've photoshopped every one of the things that I've shown you, because I'm a scientist and therefore a liar, as some people want to say us scientists want to lie. Well, I'm not lying. Here's the actual solid evidence for you. All right, elsewhere. In the Stewart Shelf, the Bunyaroo Formation, there is the debris. It's very easy to spot because it's made entirely of volcanic grains, entirely of dacitic volcanic grains. The occasional quartz grain as well, which by the way suggests that there were sand dunes, desert dunes around the place, as they would have been at the time. And at 470 kilometres away, it's just 2 grains thick. There it is. But if we go to this one here in the Flinders Ranges, the Donkey Gully, brought home a sample like that's 10 centimetre scale down there. That's quite a lump of volcanic rock. Indeed, that's the problem originally. For 2 years I believed it was due to a volcano. For goodness sake, volcanic rocks are due to a volcano. Look up any textbook. Huh? Volcanic rocks come out of volcanoes. So where was this volcano? Well, it had to be to the west because most of this thinned out to the east. But where was this huge volcano? So I never found a volcano. And the more I looked, the more a bit frustrated I became, because big rocks like that in a volcanic eruption don't end up more than a few kilometres away from the vent. Volcanoes don't tend to blow sideways. They blow upwards, so you have a steady decrease in grain size, a steady decrease in thicknesses of the layers, etc. As you go away, the ash thickness thins off in the distance. Well, where was the volcano? So after 2 years of frustration, I realised something was wrong, and so did my colleagues and friends. Peter Haynes especially was very keen on the thing, and he and I got the ideas and so on. Eventually I said, look, it's got to be a big bang out from the sky. I happened to have heard a talk back at Melbourne University days of a person coming out from the US talking about craters on the moon. And he introduced us then to the fact that you had this geological process, or astronomical geological process, that creates craters and that creates debris. So I guess somewhere in my back of my mind, in the subconscious or whatever, so I had a good sleep on it, and so I said, no. I eliminated all the other possibilities. It wasn't, the butler had to do it, whatever. It wasn't this, it wasn't ice, it wasn't falling off a cliff, it wasn't fluvial, it wasn't It wasn't even volcanic, so what else could it be? Well, it had to come out of the sky. The energy had to be on the surface somewhere, and bang, resulted in the spread out of the volcanic debris. Already at that time, the dating of the debris that we'd sent to Canberra for the shrimp, individual zircons were dated, and the people there analysed some 30 specimens for me, free, expecting to have a good result for the date of the Flinders Ranges. Sorry, busters, we didn't get a free date out of that one. And then I made a phone call. I said, oh, I think I've got a new idea, Bill Gostin. I said, I think it's to do with the sky. It fell out and meteorite. I said, oh yes, so he's telling me another one. He rang me again a bit later. He said, well, actually all the specimens we analysed, most of them had shock features in them. I said, oh, why didn't you tell me? And so there already was a recognition that the zircons they were trying to analyse for us to date, they picked the best ones, which were least shocked. You see how research goes on. You're misled, and then you're led, and you're misled again, and you try and fit the data into some existing theory, which just makes simple. I mean, it's got to be volcanic, hasn't it? No, it mustn't be volcanic. It can't be volcanic. So in the end, Constant and others published a paper saying, you know, zircon evidence for meteorite impact, the shock impact and so on. So they had their own publication out of it at last. Okay, there is the Wallace, Malcolm Wallace, who joined us. He's now a sedimentology lecturer at Melbourne University. But back in '89, he already published a paper with several of us showing the thickness variation to 80 kilometres, 304, 370, 385 and 473, progressively getting thinner and thinner as you go away from the Acraman impact site. Not only that, it actually had features here. You can see the cross-bedding, that shading, and the debris here. Two distinct layers. One with the coarse layer at the bottom. That was sort of the original debris being thrown out. Then comes the finer material settling out of the atmosphere, field height, but with the atmosphere. And then comes a tsunami, giant tsunami. So we have evidence that in fact the seafloor was swept by giant tsunamis, and that redistributed the sand. So if you were to walk along in the Bunyaroo Gorge, Brashna Gorge Valley of the Bunyaroo Formation, you'll see this particular layer come up to about a foot thick, 30 centimetres thick in places, just sand, clearly, and the top of it is rippled to show that it was formed by waves. So there's the evidence for the tsunami, the marine waves that followed the intense earthquake. By the way, just think that earthquakes on Earth, earthy earthquakes, have a limit in terms of their size, thank goodness. You know, 9 is about the limit. Japan was hit by a 9 force earthquake, but simply because the Earth can't cope with more stress than that. That's the limit of rock strength. Rocks are simply not strong enough to have anything more than force 9. The energy imparted by this impact would have made the seismic thing to force 13. So, you know, when you get hit by something from outer space at average of 20 kilometres per second, asteroidal movement, then you're in, and half mv squared, remember, energy is half mv squared, so it's the velocity squared. Never mind the mass, it's the velocity squared. So with the high velocities, you've got this amazing amount of energy. So even from a diameter of 4 to 5 kilometres diameter, you create this tremendous blast that spreads debris 450 kilometres in around. Okay, there's some of the extra features. That's in quartz. You have again the quartz lamellae. And a friend of mine, Marek Zbik, who dissolved the rock, the silica, and ended up with the zircon. And he said, Vic, have a look at this. And there, even the zircons, which don't have any cleavage, show you this pattern of fracturing that occurs with intense shock. These are all glassy. People ask me, do you ever have evidence for glass? Yes, there's evidence for glass. These would have been glassy before they were replaced by calcite and barite, I think, anyway. So calcitic replacement of the glass. The glass didn't last very long. It was replaced. And of course, at the time, one of the key features, and this was found by Alvarez and his son, or dad, father and son, Alvarez Jr., Alvarez Sr., who decided to look at the ocean sediments. They thought about this, well, we're getting some asteroidal, we're getting some debris coming in, the shooting stars and so on, bringing in material from space and some sort of average. If we were to analyse the geological sequence and we were to find the rate at which you had the iridium and platinum group elements recorded, wouldn't that give us a measure of the period of time? Very logical, assuming that everything was steady. They went to Gubbio and, in Italy and went through the various layers, and they had this amazing anomaly, bigger than this. And they said, wow, this is so big, it's impossible that there was all that time lost in that. You see, on the assumption that it was steady time, steady impact, you would then have an enormous amount of time represented by that level to record such an abundance of iridium and platinum group elements. But you had the abundance of iridium and platinum group elements, but no obvious time break. So it had to be an asteroid, and that's what gave rise to the idea of the end of the dinosaurs, was the end of the Cretaceous. They had to find then the shooting gun. They had to find the smoking gun. Thank you. You had to find the smoking gun for the increased in iridium and platinum group elements at the end of the dinosaur period, end of the Cretaceous. In my case, I sent off the material to Reed Keyes, who was in Melbourne and had a laboratory which was able to measure parts per billion. Parts per billion, 1 part per billion. He said, Victor, I hope you take off your wedding ring when you sample, because I can measure that gold that you've got on your hand as you handle the rocks. I said, really? He said, yes. It'll contaminate my lab, so don't take it off when you sample for me. So anyway, he did come up with this, and this is part of Keyes and others publishing the results below. There's a bit of an aura around it, an extension of the iridium, which shows that it does migrate to diagenesis. Okay, let's move on. So, the paleogeography at the time, I kind of already mentioned this, we did have some apparent glacial deposits in Tasmania, certainly up in the Kimberleys, and perhaps Australia, in present-day Australia, could be rotated into that sort of way. There's the equator at the time, and we're doing 10 degrees, 12 degrees north of the equator. So being equatorial or subequatorial, the impact would have affected both hemispheres. And that's important to think about from the environmental point of view. Years later, I was in Perth, and Kath Gray, and David McCurdy shares a room with me, so he's an organic geochemist, he does this, but Kath Gray looks at microfossils in the Precambrian of Western Australia. And she literally dragged me into her office and said, Victor, come here, look what I found. And she went through her folio, showing me that you have these very dumb-looking, simple, round things here. Then you had the meteorite impact layer, which she could recognise, and all of a sudden everything started growing spines and wiggles and so on. It was really some burst of evolution that occurred. He said, well, there it is. There's a biological effect. I didn't expect any biological effect, but there is the first evidence for me, for us, that there was a biological repercussion, clearly, of the actual impact itself. David McCurdy studied steranes and carbon-29, carbon-27 ratios, and again, he showed in the Amadeus Basin and the Officer Basin, he showed that it was very low ratio, but then the ratio went bizarre and great over here, so you ended up having lots of complex molecules created, biological molecules created. So again, this is the next bit of evidence that there was a burst of biological activity in the ecosystem. Let's try to put pictures together. Again, the coronine. By the way, coronine is a product of combustion. Combustion. What burnt? What was there to burn there? this has not been reported on properly, and it has not actually been thought about enough. But clearly from his evidence, from McCurdy's evidence, there was enough on the landscape in terms of mosses and lichens and, what else do you want to put? Mosses and lichens, I've got a stock about there, some bacterial slimes and sludges that burnt enough to give you soot. Soot. Well, that's something interesting, isn't it? So I think we've got a lot to discover here, leaving it to the younger generation to do that. But anyway, so there we are, quite exciting stuff, and it shows quite a polycyclic aromatic hydrocarbons, pH, an anomaly there, straight after the meteorite impact ejecta. In fact, from detailed studies, I'm coming to the end of the talk, don't worry. The impact ejecta, if we have the delta C13 ratio is the negative of it, really, is a feature. Delta C12 is product of biological activity. C13 is the stable one. C14 we won't talk about. That's radioactive carbon that's long since gone. It doesn't last more than 40,000 years. But C13 and C14 sorry, C12 and C13 are the ones we want to look at. And there's quite a fluctuation. Now maybe this is, we need more material. As I said, we did have tilt pellets to this point. There's the Acraman impact ejecta layer. And here, David McCurdy, an Aruri student, and Webster, another student of ours, compared with the Carnic Alps. So this is the Permian and Triassic variations of delta C13. Again, at the end of the Permian, there was a major collapse of the ecosystem, and there was an interesting wiggles here, and we're comparing those wiggles there. Maybe yes, maybe no. It's all kind of guesswork, but we think we might be right. And so, coming to almost the last slide, we now have the Geochemical correlations, which George Williams insists that I put this in. What this does is basically says, okay, we have well known around the world the Acraman glaciation of around about 630 million years ago. We had the younger of the two ice ages. And by the way, these two ice ages gave rise to the hypothesis of snowball Earth, which Americans took up very nicely. It's a lovely theme, made the front page of Scientific American, but I think it's all bull dust. Sorry. Not true. Those of us working on glacial deposits say, well, where is the evidence for the 1,000-metre drop of sea levels that would have resulted from a snowball Earth? Where is the evidence for the recovery? Initially they said, well, the volcanic rocks that gave rise to the ironstones came afterwards, and that deglaciated the surface and allowed Earth to return to normal. Well, sorry, but in the Flinders Ranges, the iron ore deposits come before the ice ages, not after the ice ages. And then, of course, we have the fact that not only is that, but we have another one, a younger one, in the Gaskiers glaciation of Newfoundland in Canada, well-known glaciation, a tested glacial deposit there, that we may have had the equivalence of here in Australia, the finer parts of that ice age that we have in the north. There may be, in fact, some more ice around at the time, but certainly then you have the Cambrian age there. So, I mean, research goes on. So basically at this stage I want to tidy up my talk and say, here's the Acraman impact horizon. We already have shown you the evidence for ice present beforehand, so it's kind of a double bang, double effect, one and the other. And ice rafting occurred during deposition of the mid-Ediacaran Bunyaroo Formation in the Day-Day Mudstone. Day-Day Mudstone is the formation in the Officer Basin to the west. Probably a local expression of a larger glaciation in the northern hemisphere. The low latitude of the Acraman impact further stressed the global environment. Now, asteroid impacts, people like Twicher, rarely themselves precipitate evolutionary crises. But if you have a major impact during an ice age, then the ecosystem is really troubled, affected, and presumably leads to extinction of some forms, creation of new environments, lots of new nutrient being added. That's also part of the deal, because we know too that when you start having nutrients, even in parts per billion, of chromium and metals resulting from the asteroid itself, you fertilise. You help to fertilise otherwise dead oceans or whatever. So there's something going on. So our frigid conditions prevailed at that time. Stresses caused by the glaciation were compounded by those of the asteroid impact, and the ensuing atmospheric and oceanographic oscillations produced a biotic crisis. Did release from these stresses help to stimulate biotic evolution? We think it did, but so what, you know, again, in science we can't prove. It's just you can say it's all a coincidence, but then how many coincidences do you have in terms of this sort of thing? At the moment, all we can do is present you with a hypothesis that yes, we have had ice ages. They weren't snowball Earth type ice ages, but certainly there were isolate areas of Earth which were glaciated at low paleolatitudes. That remains an enigma. And then we have had everything recover from that. So there we go. And if you go to Brashna Gorge Geology Trail, you'll see the same diagrams that I drew for you here, displayed on this called the Space Connection. This is at the, just as you come through the gorge of the ABC Range quartzite, you're driving to the west through Brashna Gorge. On the right-hand side is a couple of displays on the Aruna Valley. The Aruna Valley, across the Aruna Valley turn-off, on the right-hand side you'll have this, and this was just taken about a week ago. So thank you very much. Ladies and gentlemen.